So in the last couple of videos, we've mostly been talking about the homology group H1 of X, which detects the presence of holes in X. But we can also define a group H0 of X, which is actually kind of simpler, but it's good to explore that a bit. It'll help to tie the whole circle of ideas together. So in this case, we're going to consider a space like this. Okay, so this space consists of, this is our space, we're going to call it X, but it consists of three parts. Let's call this part A, this part B, and this part C. And so we're going to define this group H0X, and it's going to be kind of along the same pattern as as H1. If you remember, H1 was defined as cycles mod boundaries. So this again is going to be cycles mod boundaries. So it's going to be Z0X mod B0X. Quotient group like that. Z0X is the set of zero cycles. So that's a set of kind of zero-dimensional things with no boundary. Okay, so as a kind of example, we can have this point A1 here, point A2, point B1, C1, C2, C3. So we could consider like 5A1 plus 3A2 minus 6B1 plus 7C3. Okay, so that's a kind of that counts as a zero-dimensional thing. I mean, points are zero-dimensional. Lines are one-dimensional, planes are two-dimensional, but points are zero-dimensional. I said with no boundary in brackets. That's just because the convention is that the boundary of a point is empty. Right? Points don't have any boundary, so any zero-dimensional thing, it just doesn't have any boundary automatically. So that's kind of spurious in this case. So this counts as an element of Z0X. And then what's a typical element of B0X? Okay, so remember, we can have a path like this, path U here, and the boundary of U, according to our conventions, right, the boundary of a path consists of the endpoints, but we count the tip positive and the tail negative. So D of U is A2 minus A1. So that means that the expression A2 minus A1, that's the boundary of something, so that's in B0X. Actually, we could also have a path, say V here. And dV is then going to be C3 minus C2. And we could also do something like D of 2U plus 3V. Okay, so it'll be 2A2 minus 2A1 for the U part, plus 3C3 minus 3C2. So this expression here, 2A2 minus 2A1 plus 3C3 minus 3C2, that's an element of B0X because it's a zero-dimensional combination of points, and it's the boundary of something. Okay, so so because of this fact that A2 minus A1 is in B0X, that implies that the cosets A1 plus B0X is just the same coset as A2 plus B0X. So these are the same cosets, and that's just actually the same as A plus B0X for any A in this set A, right? I mean, if I've got any point A here, I can always choose a path. Wholly within A from this point A1 to A. So A minus A1 will be a boundary, and so A plus B0X will be the same as A1 plus B0X, right? Any point in this set A, set capital A, can be connected to A1 by a path, and because of that, you always get the same coset. And so the notation, you typically write square bracket A, for the coset A plus B0x. So square bracket A is the same as square bracket A1 for any little a in the set capital A. And similarly, square bracket B is that's the same as B1 plus B0x, or square bracket B1 for any B and B. And again, got a point B here, can always choose a path from B1 to B, and that gives me that B minus B1 is a boundary, and so get the same coset, right? So any point in capital B gives me the same coset, and again, square bracket C is the same as square bracket C1. And using this, we conclude that our H0x is a set of combinations like so for example, this thing that we wrote before, and this gives us a coset, but that's just you've got kind of got 8 things in A, and they all count the same, so that's 8 square bracket A1. And then 6 square bracket B1, and then you've got 7. It was C3, but C3 is the same as C1 here, so that's 7 C1. Okay, so every element in H0x can be expressed in this form. So this is just isomorphic to the group Z cubed. Okay. And of course that's completely general. Whenever you've got a space, let's maybe write this on a separate piece of paper. With the xi disjoint and topologically separate, and each xi is path connected, and so you can get from any point in xi to any other point by a path. Then your H0x is going to be isomorphic to Z to the n. There's one copy of Z for each component xi. So that's how H0 works out.